3 o'clock. Welcome to Learning Machines seminars at RISE, and especially welcome today to Professor Tuomas Virtanen, who is visiting us from Tampere University in Finland, where he is head of the audio research group. Tuomas received his PhD in Tampere in 2006. He's been a research associate at Cambridge University. He's also recognized for contributions in single-channel sound source separation, noise-robust speech recognition, and music content analysis. More recently, he's also been working on sound event detection. So without further ado, please, Tuomas, the floor is yours.
Yeah, so thanks a lot for this opportunity to present some research findings that I've been working on in the last year. So this talk is about machine learning for acoustic scene analysis. So I will first start by describing some basic machine learning tasks that are commonly used to analyze acoustic scenes. And then I will also talk a bit about, obviously about the machine learning methods themselves, then a bit about the data, because that's obviously important when you work on machine learning. And then in the second part of the talk, then some advanced methods like on audio captioning, zero-shot learning, domain adaptation, and these sort of things. But okay, let's start first by thinking like what kind of information we could be then analyzing by machine learning in everyday soundscapes. So by everyday soundscapes, I mean sounds that you encounter on a street or in office or at home or when you are in cafeteria. So obviously, sound contains lots of information, what's happening there. And if we start to somehow try to categorize what kind of things we could be analyzing. So first we could start recognizing what are the sound sources, possibly then attributes. Then obviously for human communication, speech is very important. We could recognize words, utterances, who are the speakers, and also the attributes of the speakers. Then we could analyze spatial properties of the environment. Where are the sound sources? What are the dimensions of the environment, for example, and other spatial attributes? Or then we could analyze some dynamic properties, like how sources change in time, for example. And I could also mention specific types of sound. Music then has its own properties that could be targeted. And in lots of information. So in this talk, I would be mostly focusing on these generic properties, so sound sources, and also on the spatial properties, because that's an area which has gained lots of research activity in the last years. For example, in comparison to speech and music analysis, which are kind of more conventional areas. And I will first present kind of three basic machine learning tasks that are studied in the field. So, so the first one is acoustic scene classification. So recognizing what is the acoustic scene. So treating all the sounds that are present as a whole. So for example, you could have a system which is input, taking audio as the input and recognizing if it's a recording from home or in a car or office or street. Then if we, so this is basically just a simple classification problem. Now if we zoom in a bit, we could be analyzing individual sound sources. What are the sources and when they are present? So typically sound sources are not active all the time. So one sound source produced one event which is only active certain time. So then often we want to know when it is active. And typical sound events that, for example, in environmental audio analysis, we could be analyzing if there is car passing by, traffic like line beep, footsteps, for example, in this image that I'm illustrating here. So this is called sound event detection. And and this visualization there in the left shows that what could be then the output of such systems. So we have events, event labels, and then the activities of them in time. And here I have an example video of illustrating the output of a sound event detection system. So the video here is not used in the analysis at all. So this is just visualizing what the system is outputting. So there in the middle, we see what is the system output. So let me play the video. So I don't know how well you could hear, at least these door sounds are pretty prominent. And this was pretty quiet environment, so we could hear even the footsteps and some speech there in the background. Obviously then in some, for example, if you have recording from a street, then you have much more things going and much more dense in events. Okay, if we then continue, then we could be analyzing where are the sound sources, so localizing them spatially. So this is basically then typically implemented as estimating the XYZ coordinates of the sound sources in some coordinate system. Often, for example, the microphone array is in the origin of the coordinate system. And naturally then sound sources are often moving in time, so this would be called tracking. And furthermore, often there is multiple sources present simultaneously. So this is then, we would be estimating the XYZ coordinates of each of the sources. So this would be then multi-source localization or tracking. And furthermore, often we are interested in actually also classifying at the same time where the sound sources are and what they are. So this would be then a joint sound event localization and detection. So we are estimating the XYZ coordinates of each of the sound sources and giving them the class label, for example, this car, speech, and beep, which have been visualized over here. And okay, just to illustrate with the video, what could be then the output of this kind of system. So again, here the video is not used in the analysis, but just to show the locations of the labels. So here we have so the events are detected events are shown with these labels that are overlaid on top of the video. For example, this music is coming from the loudspeaker. So if I play it over here, actually now I don't hear it myself. For some reason, the audio is now missing from this one. But I think you got the idea even by seeing this video that, I mean, we are then basically then localizing events spatially and then estimating the temporal activities. Okay, so basically these are the three basic machine learning tasks that are typically used to approach acoustic scene analysis. So classifying, acoustic scene classifying to recognize what is the scene, then sound event detection to detect individual sound events, and localization to estimate their locations, and possibly then also detecting at the same time what the events are. To give you some idea, I assume that not many of you have audio background, so give you some idea like why we are doing this. I will give some brief overview of different applications of these. So first, some general kind of motivations of audio-based scene analysis in general. So obviously, different sensors produce different kind of information. In case of audio, the strength is typically that when something is happening in an environment, some physical activity that typically produces sound. So then physical activities can be often recognized based on sound. In comparison to video-based analysis, audio analysis is typically computationally much more cheaper and less intrusive. Obviously in audio, there is for example, speech often, which contains can contain sensitive and personal information. So obviously then that's something that may need to be handled depending on what kind of applications you are working on. And of course, audio doesn't really depend on the lighting conditions or doesn't require line of sight to the sources that you are interested in. One big application area is context-aware devices. So this basically means that a device such as a hearing aid or smartphone will recognize what is the environment it is in based on audio. So for example, for hearing aid users, it's useful to know if the user is in, for example, in quiet environment, or if the user is listening to music, or is in some noisy environment, trying to listen to speech, and change the processing mode based on that. And similar thing, for example, in smartphones. Then on the other hand, devices like autonomous cars or robots, they benefit from knowing what's going on around them. So for example, an autonomous car could, if it hears children laughing from behind a corner, it could then slow down or warn the driver. Perhaps the biggest application area is acoustic monitoring. So there is several areas there. So for example, in smart home applications, like things that we could be detecting if there is a window breakage or somebody knocking on a door, or fire alarm, or baby crying, or dog barking. Then in smart cities, for example, sirens, gunshots, or accidents, sorry for that, are often detected based on audio. Then in bioacoustics, based on audio, we can recognize what kind of animals are present in an area. We can monitor a large area just using a single microphone, or analyze the animal behavior. Or in machine condition monitoring, we can analyze then if a machine is about to break. And in health monitoring, for example, now in this COVID times, we could be analyzing like how much coughing there is in certain environment, and what kind of coughing even. And for example, in my group, we have been doing some automatic detection of epileptic seizures based on audio. Or then if there is an elderly person living alone, then monitoring the status of that person. So lots of applications there. Then there is also application in assistive technology. So for example, automatic captioning of sound events in YouTube videos has existed already quite some time. Or then you could do multimedia information retrieval. So find your favorite cat videos from social media based on audio. Okay, so then after this short motivation, I will present this general machine learning approach for acoustic scene analysis. So obviously, as in many other fields, these methods are often based on supervised learning. So for training the methods, you have audio and the corresponding target output. For example, as is visualized in this image, you have the audio and the target output of a sound event detection system. And of course, then we need large quantities of this audio and target output. I will discuss a bit later, like what kind of data we will need specifically. And obviously then this limits us to certain predefined sound classes when we are using supervised learning. So when we collect the data, we define what are the classes, and that limits the system to analyzing only those. During the second part of this talk, I will be discussing some advanced methods actually that go beyond this limitation, but this is in most methods that are applied. Okay, so the general approach is that we have audio going to the system, then we have the feature extraction, and then with the machine learning part, for example, if it's doing classification, then outputting vector, which where the elements correspond to the probabilities of different classes. Now, if we do detection, then where we include there the temporal dimension. So we estimate the temporal activities of each of the classes that we are interested in. And in localization, we are then typically estimating the XYZ coordinates of each of the classes, so separately, that we are interested in. Maybe at this stage, I should discuss a bit like what kind of input, microphone input we need to use in this kind of systems. So for classification and detection, it's enough to have a single microphone. But for localization, to analyze the spatial information, we actually need a microphone array. So basically multiple microphones operating together. Luckily, those are quite commonly available. For example, in smartphones, you typically have a couple of microphones, and for example, in smart speakers, there can be 6 microphones in some of them. So this is not a limitation. So many commercial devices actually include a microphone array. Okay, you might be wondering now, in this general machine learning approach, I had here this specific feature extraction part. So why do we need to then do specific feature extraction? Why can't we feed in just raw audio and let the machine learning system then learn the relevant features, for example, with some convolutional layers? And okay, you can very well feed in just raw audio, and yes, you can let then the machine learning part learn the features. But I would say that the biggest reason why we are actually using some manually engineered feature extraction is the computational complexity. Because in audio, the information is typically best present in some spectral representations. So what if you let a convolutional neural network learn the features, then what you end up having is then a convolutional kernel corresponding to some time domain filter. So you end up learning a filter bank, which is on the other hand very inefficient computationally because you did convolution in time domain. So instead, what we do often is we just calculate some spectral representation, for example, using fast Fourier transform, which is computational more efficient, and then we let the deep learning, for example, convolutional neural network learn from those. So in case of single channel methods in classification and detection, so the most commonly used feature is the MEL spectrogram. So that's basically representing the energies of the sound in time and frequency in this so-called MEL band. So MEL resolution is something somewhat similar to human perception. So the resolution is not uniform in hertz. And so it corresponds roughly to the distribution, how information is distributed in natural sounds. And I would say that in 95% of the cases, this is very good feature. So whatever classification task you start solving. So this is, I would say, what I would recommend as the first feature to try out. And then you can let the convolutional neural networks to extract more high-level features based on the MEL spectrogram. In the case of localization, so when you are operating with multiple channels, then you want to have features that somehow encode spatial information. So that could be, for example, phase spectrograms of all the channels, or phase differences between all the channels, or correlation between channels, or covariance matrices. And so this is actually an active research area at the moment. So new features are developed here. And this is in multi-channel audio, these manually engineered features are, I would say, even more relevant than in single channel, because in case of multi-channel audio, you have the amount of data is even more. So the typical sampling rate of audio is, for example, 44.1 kilohertz. And if you have 6 channels, so that's quite a lot of data to be processed. So that's why you want to have some manually engineered features to make this sort of systems efficient. Okay, once we have extracted the features, so the typical first processing blocks are then convolutional neural networks. So I mentioned those already a couple of times. So they operate similarly as in machine vision. So basically we are treating then the spectrogram as an image, and then we let the convolutional filters learn some relevant patterns from that. And of course, we then typically stack multiple convolutional layers and use some subsampling and nonlinearities in each layer. And in the end, for example, if we are doing classification, then we are stacking the features and often have some fully connected layer to map to the number of outputs that we want to get. In the case of audio, what is then specific? Okay, so these first stages are quite similar to what is done in machine vision. So, but what is then specific to audio, what is different from many other machine learning tasks that we often we need to do some sequence modeling to model the temporal context. And this is needed, for example, because if you analyze just small pieces of audio, it's often difficult to tell what are the sounds based on just one short segment. You need to model a longer temporal context. And there is several machine learning models that can be used. For example, recurrent neural networks are very commonly used, which are visualized in this figure. So there in a recurrent neural network, then you add connections in time to pass information, for example, from past frames to the future. Now, recently then attention and self-attention have also gained lots of research activity. For example, you may have heard about transformers, which are these kind of self-attention models. So in attention models, then you basically then are combining inputs from different times, and then this attention then tells you then like how to weigh each of them to make the final decision for a certain time step. And in this self-attention, then you're basically then calculating similarities or correlations of features across time, which allows then modeling the temporal structure of sequences. Then dilated convolutions are also an effective tool. So they are basically then allow using larger receptive fields. So what is different in them is that in dilated convolutions, okay, the receptive field is larger, and you could say that they can have then holes or basically zeros in the convolutional kernel, which then allows modeling larger temporal context with a smaller number of parameters. So these are important in the case of acoustic scene analysis, so proper sequence models. And actually here then I'm visualizing a convolutional recurrent neural network. So of course then what you can do is you can combine different kind of processing layers. So what we typically do is that you first have a number of convolutional layers, and then after that some temporal model. For example, here we have a recurrent neural network for modeling the longer temporal context. And then you can stack these different kind of processing units and do end-to-end learning, so optimize all the parameters of this network at once. And this kind of CRNN structure, I would say that's baseline structure that we have been successfully using in many different problems related to, for example, sound event detection, localization, and many others. Okay, some words about then task-specific processing. So starting from acoustic scene analysis, so I already showed this figure. So this is basic classification problem. So then what you need to do at the final layer is just then fully connected layer and then mapping to the number of classes that you have, and with softmax max activation so that you get the probabilities out from your system. In case of sound event detection, then this can be implemented by then classification in consecutive temporal segments. So you split the audio in segments and classify in each of them what are the active classes. But here it's useful to use intersegment contextual information. For example, have then recurrent network passing information from the past to the future, for example. And in sound event detection, we often want to handle multiple sounds at the same time. So this is basically then a multi-label classification problem. And this can be implemented easily by replacing this final softmax layer by sigmoid units. So nothing too difficult there. Now, in the case of localization and tracking, so like I said, this is basically estimating the XYZ coordinates of each of the classes. So then Now these coordinates XYZ would be the output of your deep neural network, for example. And so this is basically a multivariate regression problem. So you typically then have just a linear layer as the last one to allow outputting arbitrary XYZ values. On the other hand, often in localization, we cannot estimate, with a single microphone array, we cannot estimate the distance of a sound source that well. So often we are just estimating directions. So then basically then these XYZ coordinates are projected to the unit sphere. So then you can have this normalization layer that projects these XYZ coordinates to the unit sphere. And if you do tracking, so estimate these coordinates over time, so then of course then can be done easily by then outputting XYZ in temporal segments and then having, for example, a recurrent layer to impose some temporal continuity or allow modeling temporal context. Now, in case of localization and tracking, there is one thing we need to handle somehow is that, and that's that often there is sound sources are not active all the time. So what would be then the XYZ coordinates in that case? And often this is then handled by having then a separate output of a machine learning system which then tells when these classes are active. So this is basically doing the detection at the same time. So, and this is now visualized there in the figure, right? So there is one output of a machine learning system outputting the XYZ coordinates in time, and another branch which is outputting then the activities. So basically binary values indicating the activity of different classes. And when we are training this kind of system, we can then mask now this regression output so that the loss is calculated only when the sound events are active. We can also encode now this two different outputs to a single output. Now in this case, when we are estimating XYZ coordinates on the unit sphere, so we can actually represent the activities using the magnitudes of this vector. So this simplifies this system structure and actually even leads to better results. So this has been successfully used in the last years. Okay, so after now explaining this basic methods, I will discuss very briefly then data, that is the effect of the data that we use to develop these systems, because obviously like how well your system, machine learning system works is often completely dependent like what kind of data you use to train it. In case of audio, there is several factors affecting the captured audio. For example, what kind of microphone is used, what kind of audio processing there is in the capture device, if there is some interfering sources, or the transfer function from the source to the microphones, and obviously the sources themselves. And there is many ways how you can then get data, like of course you could try to do real recordings, annotate them, and this can be often very slow and laborious. On the other hand, you could try to synthesize material, but then it leads to questions like how well then your system will work if you synthesize. And of course, you could manipulate and augment some existing data. And often, I would say then to get good methods, then you should aim at having then realistic diverse material, and which somehow then sample different factors that you can encounter in the data. And then if you then if your data then covers enough different factors, then you can expect that it will generalize to even to some new conditions. And just to give you an example, for example, for acoustic scene classification, so this dataset that we have collected in my group is How Urban Acoustic Scenes 2020 Mobile. So this was used in this international decades evaluation, which we have been active organizing. So this is environmental recordings from 10 different acoustic contexts, so airport, shopping mall, metro station, pedestrian street, and so on. And okay, in order to get the sample, then different variability geographically, then we collected data in 12 large European cities in Amsterdam, Barcelona, Helsinki, and so on. And to get enough diversity, we even recorded data in several different locations in each city and each class. And to get diversity in terms of recording devices, we recorded 4 different devices in parallel. So binaural microphones plus 3 mobile devices. And this dataset, if you want to try this out yourself, it's you can find the link from this DK's website that is there below. And okay, just to give you an idea, this map here is visualizing the recording locations in London. So we really had research assistants traveling to quite many places and doing recordings. So this was quite big effort to do this data collection. This video here is illustrating one acoustic scene. So, and yes, actually we also recorded videos. So this is a video from London. At least now I hear the audio myself. So, okay, so it was just a problem with this one particular video.
I have a question, Thomas.
Yep.
How do you go about annotating these recordings?
So in the case of acoustic scene classification, that's easy because basically the scene is defined by the location. So if a person is on a street like here, then it's enough to know what was the recording location. So in the case of acoustic scene classification, this is relatively easy and doesn't require much work to basically just indicate which of the possible acoustic scenes the recording was done in. In the case of sound event detection, we have been also then, that basically requires the manual work to spend time listening to the recordings, annotate when different events are active in a recording. So that's much more slower. Okay, regarding this dataset, I want to mention that, okay, also these videos are publicly available. So if you want to use this for your own research, so then you will find the link from this DK's website. So, and these are freely available for research purposes. Yeah, okay, I mentioned that for sound event detection, it requires then manual annotation. So that's then very slow. So people listening to the recordings indicating when the sounds are active. And that's why often crowdsourcing is used there. And then you on the other hand, you need to have machine learning methods that can deal with these noisy labels, for example, that one can get from crowdsourcers. Okay, in case of localization, the annotations is even more difficult because you need to then indicate what are the XYZ coordinates of the sound sources. And this is very difficult to do manually. So what, for example, what we have been doing in my group is then using video together with audio. So with video, we can then get reference locations of the positions of the sound sources and can even use some visual tracking systems to get automatically the locations. So this can be beneficial. But even then for sound source localization, for training the methods, then often you may want to use some simulation. So what we have been doing in my group then, developing methods to effectively simulate acoustic scenes. So then this consists of then measuring, for example, impulse responses in real rooms, and then for example, doing measurements like this. So, okay, what is, for example, visualized here. So here, let me play the video. So here, this is a measurement from a lecture room. And what you see there's these circles indicate the locations of a loudspeaker producing a measurement signal, which is then moved around this room. So we are continuously measuring there the impulse response from that location to the microphone, which is there actually. This is a from a video, 360-degree video where the microphone is then under the video camera. So it's measuring the impulse response between these two. And once we have done these measurements in several different locations, then we can actually simulate sound events in many different locations of these environments. So we combine random sound events with random locations and can create some acoustically realistic acoustic scenes this way, a lot of them. Okay, so after discussing the data, I want to then spend some time discussing kind of more advanced machine learning topics. I expect many of you are interested in this. So first, like how we can analyze more detailed information about acoustic scenes by captioning, or how we can go beyond this predefined categories to analyze some new arbitrary classes by zero-shot learning, or then how we deal with this bottleneck of training data by doing active learning, or how we can then deal with training test mismatch by domain adaptation. Okay, if we start from audio captioning, so that's basically in audio captioning, the goal is to produce a textual description of an audio signal. So for example, here in the right, you see possible description of an audio signal. So then the idea there is that we can, by captioning, we can present more rich information that goes then beyond just some classification or recognition tasks. And it can model, for example, relationship of sources, multiple sources, temporally or spatially, or then we can describe attributes of the sources and the environment. Now, in captioning, we have the problem that how an acoustic scene is described then depends on the listener. So different people then, of course, describe an acoustic scene in different ways. So how we can get then material for developing methods for this purpose. So we have been then doing crowdsourcing to collect data set of audio captioning. So this consists of then first asking annotators to produce initial captions. Then we have another set of workers to edit them, fix the language, and then a third set of annotators then to score these different captions that we got. And this way we can then, with this procedure, we can guarantee that we can get then the rich and diverse captions for audio describing acoustic scenes. So for example, here, this is illustrating now 5 different captions of the same audio signal. Let me play it. I would say that all of these are correct, and then we can use all of these then to do machine learning to learn different properties as we want. Okay, so from machine learning point of view, then captioning is a sequence-to-sequence mapping problem. So we have the sequence of audio features going in, and we want to output a sequence of words. This is now different from, for example, event detection in the sense that this is not synchronous mapping. So in event detection, for one segment of audio, we were targeting to estimate what are the activities, active classes in that specific segment. But in the case of captioning, there is no really straightforward relationship that the one input audio would correspond to one word. So this is highly complex mapping, and there is large differences in the length of this input and the output. So that's why we need to have more advanced methods to deal with this. And the typical approach is then to use encoder-decoder structures. So we have first an encoder, which is typically quite similar to what I presented earlier. So first some convolutional layers and subsampling, and then it outputs a sequence of feature vectors. And as the decoder, for example, we can use recurrent neural networks, or what is our best result is then based on transformers, so this kind of self-attention methods. So then these methods then figure out then how different parts of the input should be weighted to, for example, produce output one word. So this allows then more effective modeling of complex relationships between the input and output. And okay, just to illustrate you like what kind of results can be achieved by this kind of system. So this is now showing both the reference or the ground truth captions and the system prediction there in the right. So let me play, for example, here this audio signal. And okay, now this captioning system thinks that it's a dog barking while birds are chirping in the background. And okay, I would say that's more or less correct. Not much to complain there. If I play the other one. Yeah, sounds like flipping through the pages of a book. Now the captioning system thinks that it's a person that is doing this. This is probably correct in this case. Then, okay, those were some good examples. So then, of course, not always the captions are that kind of detailed. For example, if I play this example here. Yeah, it's a door open and closed, but maybe there could be more information. It sounds like some rusty door or something like that. And of course, like there is cases where it then fails. So if I played, this is a quite funny example. So if I play this one. So now the captioning system thinks that this is a person uses a knife to sharpen a knife, even though it was some bird sounds. And okay, I can kind of understand where this is coming from because for example, if somebody is sharpening a knife, it can produce some sounds that are somewhat similar to this bird chirping. But for example, now this even this sentence like uses a knife to sharpen a knife. Maybe if I were to sharpen a knife, I wouldn't use a knife to do that. So then maybe now this captioning system doesn't have full understanding what sharpening knife then means. So, but okay, this is very active research area at the moment. There is lots of room to improve these techniques. Now, if we move on, then one of the limitations often is in the training data. So the training data is often the bottleneck, especially annotating the audio. Audio is quite often easy to record, but then manually annotating that often takes lots of time. And active learning is one good approach to deal with that. So what active learning means in this context, that the machine learning system actually itself figures out which part of the audio dataset should be labeled in order to improve the machine learning system. And the approaches that are used, and it commonly involves some unsupervised learning somehow to organize some large audio datasets that we have. And then this actual active learning part, which then estimates which samples should be annotated, and then training the actual machine learning model. And often this is an iterative process. So first some samples are selected to be annotated, and the model is updated based on that. And then based on that, then the machine learning, active learning system then estimates a new set of samples to be annotated optimally to improve its performance. But this approach can be very effective. So for example, in our experiments in a good scenario, we have shown that it's enough to annotate only 2% of the data to get the same performance that then this kind of fully supervised learning system would require, which then requires then annotating all the trained data. So it can be highly effective in optimal scenarios. Then handling, okay, those of you that have been working on deep learning probably know that mismatch between training and test data is one big problem there. So you can have a method that works very well if the test data is similar to your training data. But if the test data is somehow different, the performance often can drop dramatically. In case of audio, these differences in training and test can be simply because if you use different devices to do the recordings, or if there is some new type of noise in the test data, some new environment. So what we have been working in my group is then domain adaptation methods that basically then try to learn features. And we have been using adversarial learning to do this. So you try to, in that setting, you try to learn features where the distribution between this kind of training features and the test, or no, in case of adversarial learning or domain adaptation, this would be called source and target data. So you want to learn some feature extraction model where the distribution of the source and target data is similar. And in adversarial learning, you do that by having a discriminator, which is trying to guess if the data is from source or target data set. And this is one effective way, for example, to do domain adaptation. And this can be done in unsupervised way, having not any labeled data from your target environment. Okay, as the last advanced topic, I want to mention then zero-shot learning, which then allows going beyond this limitation of recognizing only some predefined sounds that exist in the training data. So in the zero-shot learning, the idea is to recognize sounds from which you don't have any training samples from. Instead, you use some semantic side information, for example, textual descriptions of the classes. So, and I think a good example of this is that if you want to teach a person to recognize a zebra, then you simply tell that person that okay, and in a setting that that person has never seen a zebra, and to train that person to do the recognition, you could simply tell that person that zebra is like a horse, but with black and white stripes. And I would guess that based on that, the person can recognize zebras pretty well. And okay, so how did this goes in the case of audio? So we have then some we have a training stage where we have some audio, and we have the side information. Now in our case, we have simply used then the names of the classes as the semantic side information, and also the textual description of the classes. So with this, we then train the zero-shot model. So basically, how the word dog is related to the sound of dog, and how the label cracking fire is related to the sound. And after that, once we have done this training, we can recognize some completely new classes from which we have only the class names or the description. So for example, now recognizing cow, wind, sneezing of chainsaw, like we only use the class names. At the inference stage, we input some audio, and the system is able to predict these new classes from which we did not have classes by modeling these semantic relationships between the class labels and the audio. Okay, some future perspective of this acoustic scene analysis. So often realistic training and evaluation data is still a bottleneck. So there is still a need for ways to effectively kind of collect and use existing data. And obviously that can involve then even machine learning, for example, how to deal with noisy labels. Then active learning is a good way to deal with the data bottleneck. So you have the machine learning system cleverly asking human annotators to annotate specific segments. And obviously then transfer learning in different forms is highly applicable. So this includes, for example, the zero-shot learning that I presented and domain adaptation, but also cross-modal learning, for example, using video data. For example, if you record in parallel audio and video, how can you use that to then develop sound recognition systems? Then one trend in the fields is going from fixed categories to arbitrary textual descriptions or some new classes. So basically audio captioning or then zero-shot learning. And naturally there is lots of active research on the deep learning architectures and especially related to multi-channel audio. Okay, now if you are interested in learning more about this research field, so there is in 2 weeks, for example, this DK's workshop on detection and classification acoustic scenes and events, so that will be organized online. So it will be easy to participate if you are interested. And related to that, we are also been organizing this DK's challenge. So this is a data challenge which provides an open data, some baseline methods, software, and metrics. So you're welcome to participate. This is a good way to get started also. And if you want to read more, there is this book published a couple of years ago that I edited with some colleagues of mine, authored by leading researchers from this research field. And then from my webpage, you will find all these publications explaining more about the stuff that I presented here. And then the datasets, for example, can be found from this DK's website. And of course, now most of this work was done by people in my research group, so I should then acknowledge their contribution. And thank you. Now I'm happy to answer whatever questions you may have.
Okay, I have a question. Thank you for your presentation, Tuomas. Very good. What about more active settings with sound, where you can send sound from a device and then collect the results? What kind of research and activities are ongoing on in that field? Are you aware of that?
This is an area I haven't been following that much myself. So like here, now these methods that I presented, of course, they are based on passive analysis. So we assume that the sound sources themselves are emitting the sound. But I have to admit that on this kind of active methods, of course, now this when we are measuring, for example, impulse responses in a room, what we did, we have the loudspeaker producing the measurement signal, and then we can measure the spaces like this. So this is basically the area I've been working myself. But other than that, I have to admit that my knowledge on this is quite limited.
Okay, maybe I can put another question while I'm having this opportunity. So when we go to attention mechanisms and transformers, is it still necessary to do this transformation into the Fourier space, or could the transformer be more suited to actually get the raw data directly? Do we know that?
I haven't seen any studies about this. I would say that if you apply a transformer on raw audio, it will be very ineffective computationally. Because, for example, if you have just 10 seconds of audio, you will have a sequence which length is hundreds of thousands of samples. So having a transformer operating on that will be highly computationally complex. So yeah, my intuition is that you definitely want to do some feature extraction and even then some subsampling in time. Because in audio, the typical frame rate is something like 100 frames per second. So then the kind of low levels features, then you have sequence lengths of, for example, 1000 frames, which can lead to then computationally quite intensive methods. So right. That's why some subsampling can be effective.
Right. I was wondering because when we do these 2D representations of the frequency contents, we actually do some sort of implicit manual feature construction by limiting the time, right? So things that could happen over longer time series are maybe not in that receptive field, sort of.
Yes, but I would say that it's usually okay to use this low level of feature extraction locally in time. And then the information that where you want to model the larger temporal context operates then at higher level.
Okay, thank you very much. I will not take more time.
You're welcome.
We have a related question in the chat. So you mentioned that MEL spectrograms are a good representation for 95% of the cases, but Konstantinos is curious about the other 5%.
Yeah, good
question. Shed some light on that.
Yeah, so I think then, for example, areas where I can see that it's beneficial to use some other representations is, for example, in music analysis, where you want to, for example, estimate accurately the frequencies, then you want to use some spectral representations. For example, constant Q representation is often used in music analysis. That's the first thing that comes to my mind. Or then, for example, if the phenomena that you are interested in is, for example, strongly related to, for example, fundamental frequency of the sound. So, for example, if we are analyzing bird singing in bioacoustics, then I could simply have some fundamental frequency estimator as the feature extraction stage. And then, for example, in speech emotion or speech, if you're analyzing attributes of a speaker, then you can have you want to maybe, for example, estimate like how harmonic a voice is, or how much roughness there is in a voice. So because this MEL spectrogram simply presents the energies in different frequency bands, so it doesn't tell, for example, like how voiced sound it is. So and in this kind of scenarios, then having some other features is beneficial. Those are a couple of examples that come to my mind.
Thank you. Do we have some more questions?
Yes, I have a question. So I was wondering about, is it common to use self-supervised representation learning techniques in audio? So that's a very common thing in vision nowadays, and increasingly so. Is that true for the audio domain?
Yes, definitely. That's very active research area. And I think it's quite similar ideas that what are used. So for example, predicting in time the features it seems to be effective mechanism for like you predict what comes in half a second or 1 second, seems to be very effective in self-supervised learning. Yes.
Thank you.
Would you say, I mean, many things take that route. So in machine learning, many things get applied to vision first, or we develop models that work for vision, and then apparently they worked also for sound. Do you have some examples where this was not the case, or examples of when something that worked for vision did not work for sound? Or when you sort of need to had to think one step more to sort of make it work on sound?
Well, I think one of the cases is, for example, this multi-channel audio processing. I explained that because of the amount of data, pure machine learning is maybe not so effective there. And that's also an area where I think this kind of more traditional signal processing approach are still being used. I think this is partly because, okay, I explained some of the issues. For example, one of the, like if you go do this multi-source tracking, like that can be formulated as a machine learning problem, but there is still open problems there. For example, like if you, okay, the approach that I presented is okay to estimate the coordinates of XYZ coordinates of one sound class, and for each sound class you estimate the XYZ coordinates. But what if you have then multiple sounds from the same class, then how would you handle with this kind of situation? So what is specific in audio in comparison to vision, that in audio we often, I mean, the signal that you record, it's a superposition of all the sources that you have present there. So I think that's something that's somewhat different than from machine vision, and at least there, then in audio, we need to then find ways to handle this kind of overlapping sources. And for example, one area which I didn't actually discuss is sound source separation. So if you have multiple sources, trying to extract the sources of individual sources, and my group has been very active also on this topic, and it can be used also in analyzing soundscapes, and of course it has applications of its own in some kind of virtual reality and augmented reality applications. And I mean, it can be done with machine learning, but it involves then research problems that are then very different from machine vision, for example.
Thank you. If there are no more questions, then let's thank Tuomas for this nice talk. Next week, we have a presentation from Diarmuid Corcoran, who is at Ericsson and KTH. The topic will be reinforcement learning for automated energy efficient mobile network performance tuning. So thank you everyone for today, and especially to Professor Virtanen for this nice talk.
Thanks a lot.